Yellowstone isn't sitting on a lake of lava. It never was. And the diagram you've seen in every textbook, every documentary, every animation of a glowing column of magma rising straight up from deep inside the Earth. That picture just got thrown out by the most detailed model of the ground beneath the western United States that anyone has ever built. What they found instead is stranger, harder to predict, and it's forcing scientists to rebuild their models of how this system actually behaves. Let's get straight into what changed, why the old theory quietly stopped working, and what this new picture actually means for the risk this place poses, because there's a lot to unpack, and it only makes sense once you see the pieces stacked in order. There are three things worth walking through here. First, why the old theory quietly stopped working, and the specific piece of evidence that broke it. Second, what researchers are now calling a mantle wind, and why it means Yellowstone isn't sitting on anything resembling a lake of molten rock at all. And third, and this is genuinely the part worth sticking around for, what this new model says about where Yellowstone is actually headed, because it has been moving slowly for millions of years, and there's something specific sitting directly in its path. First, the basics, because half of what people assume about Yellowstone is wrong from the first sentence. Yellowstone isn't a mountain. When you picture a volcano, you picture a cone with an opening at the top. Yellowstone doesn't have a cone. 34 by 45 miles across, so enormous that when you're standing inside it, taking pictures of elk and bubbling hot springs, you don't feel like you're inside anything at all. The rim sits beyond the horizon. That kind of hole is called a caldera, and a caldera forms when the ground doesn't explode outward. It collapses downward because everything that was holding it up underneath simply left. Yellowstone has collapsed like that twice in the last 2.1 million years, once around 2.8 million years ago, and again roughly 630,000 years ago. Each of those events threw somewhere between 1,000 and 2,500 cubic kilometers of rock, as the 1980 eruption of Mount St. Helens, the one that flattened forests and dominated the news for a month, was about 1 cubic kilometer. Yellowstone's smaller of its two caldera-forming events was still in the ballpark of 1,000 times larger than that. Anything over 1,000 cubic kilometers gets its own classification, a super eruption. There are only about 20 places on the entire planet even capable of producing one. It's worth putting that scale into a slightly different frame. If you tried to picture 1,000 cubic kilometers of material sitting somewhere on the surface, you'd be looking at a cube roughly 10 kilometers on each side, more than 6 miles in every direction, made entirely of ash and rock. And that's the smaller of Yellowstone's two. Documented super eruptions. That volume didn't stay in one place either. Ash from Yellowstone's past eruptions has been found preserved in sediment layers as far away as the Gulf of Mexico and the Midwest, which is part of why scientists can reconstruct the timeline and scale of these events at all, long after they happened. The reason this matters isn't really the crater itself. It's what a super eruption puts into the sky afterward. Ash and sulfur dense enough to dim sunlight and drop global temperatures for years, disrupting agriculture on a scale that would ripple across the planet. That's why understanding this system and understanding it correctly actually matters. Now here's the part that's a little uncomfortable to admit. For 50 years, the standard explanation for what powers Yellowstone was wrong, or at least incomplete in a way nobody could resolve until now. The old theory was called a mantle plume. Picture a lava lamp. You heat the bottom and a blob of hot wax detaches and rises straight up in a column. The idea was that the Earth does something similar, a plume of superheated rock rising from deep near the planet's core, burning its way up through the crust like a blowtorch aimed at the underside of North America. Thud. T-theory had one very strong point in its favor. Yellowstone sits in a genuinely strange location. Almost every volcano you can name sits along the edge of a tectonic plate. Think of the Pacific Ring of Fire and its subduction zones. Yellowstone sits nowhere near an edge. It's parked in the middle of a continent, 1,000 miles from the nearest plate boundary, and it's still erupting. A blowtorch rising from deep below was the obvious way to explain a hotspot sitting in the middle of nowhere. But the blowtorch theory made a specific prediction, and that prediction kept failing to show up in the data. A blowtorch produces a narrow, focused hotspot, a single point. What scientists actually measure underneath Yellowstone is broad, lopsided, and tilted. A long, smeared streak leaning off to the southwest rather than a tight dot. On top of that, seismic imaging, essentially a CT scan of the Earth built from the way earthquake waves travel through different materials, kept coming back ambiguous. If there were a clean, continuous column, men of hot rock running from near the planet's core all the way up to Yellowstone, it should show up clearly in these scans. It never did. For years, that was treated as an awkward footnote, something researchers knew didn't quite fit, but lacked the computing power to properly resolve. It's worth sitting with how strange that gap actually is. This isn't some remote, poorly instrumented volcanic system in a hard-to-reach corner of the world. Yellowstone is arguably the single most intensively monitored volcanic system on the planet, wired with more seismometers, GPS stations, and gas sensors than almost anywhere else on Earth. Decades of data kept quietly failing to confirm the one prediction the leading theory actually depended on. That's not a small inconsistency to carry around for 50 years. It's the kind of gap that, once someone finally had the computing power and the modeling techniques to properly resolve it, was always going to produce a genuinely disruptive answer. That's where the new study comes in. A team built a high-resolution three-dimensional simulation of the entire western half of North America, modeling both the rigid outer shell of the planet and the slow-flowing layer underneath it, then let the model run forward using real, present-day physics. What came out of it was that the heat-feeding Yellowstone isn't rising from deep below at all. It's arriving sideways. To understand why, you need two layers. The lithosphere is the outer shell, the crust plus the very top of the mantle, rigid and brittle, essentially the plate itself. Beneath that sits the asthenosphere, still technically rock, but hot enough that over long stretches of time it flows almost like glacier ice, solid to the touch in any given moment but capable of slow, continuous creep. What the new model shows is that this asthenosphere layer isn't sitting still beneath North America. It's flowing horizontally, sweeping eastward inches at a time in a pattern researchers are now calling a mantle wind. The word wind is doing a specific kind of work here, and it's worth being precise about what it does and doesn't mean. This isn't air movement, obviously, and it isn't even remotely as fast as anything we'd associate with wind on the surface. It's a slow, continuous, horizontal current of hot rock, moving at a scale of inches per year rather than miles per hour. But the comparison to weather is useful because it captures something important. This flow isn't a fixed, static structure sitting in one place. It's dynamic, shifting, and shaped by forces happening elsewhere on the continent. The same way weather in the atmosphere is shaped by pressure systems and temperature gradients far from wherever you happen to be standing. What's driving that flow is essentially a ghost. Millions of years ago, an oceanic tectonic plate called the Farallon Plate was sinking beneath North America. That plate stopped existing at the surface a long time ago, but its descent is still steering the deep mantle flow today. In effect, Yellowstone is being fed by the wake of a plate that vanished from view long ago, which is part of why researchers describe this as a kind of ghost signal driving the system, rather than an active, visible structure. Here's the clever part. That flowing rock is genuinely hot, but it isn't liquid, and that distinction matters enormously. So how does it melt? Not by adding heat, by taking away pressure. Picture a sealed can of soda, warm but with no bubbles forming, because pressure is holding the dissolved gas in solution. Crack it open and it foams instantly, not because you, aided it or shook it, but because you dropped the pressure. Rock behaves the same way. Deep underground, it's squeezed so hard it stays solid even at extreme temperatures. Let it rise even slightly and that pressure releases, and it melts right where it sits. Geologists call this decompression melting, and it's arguably the single most important concept in this entire story. As the mantle wind sweeps eastward, the hot rock gets nudged upward, decompresses, and melts near the top of the asthenosphere. That melting happens shallow, not deep. The furnace underneath Yellowstone was never a narrow chimney rising from one central core. It's a sideways draft that melts itself as it travels. So why isn't there a lava lake down there? Melting the rock is only half the puzzle. That melt still has to get through the lithosphere above it, and the lithosphere is solid, cold, and thick. This is the second half of the finding, and arguably the more consequential one. The mantle wind pushing eastward doesn't just carry hay. It physically shoves against the plate above it. At the same time, opposing forces are pushing back from the west. Two forces, opposite directions, acting on the same slab of rock, and the plate caught between them stretches. Think of pulling apart a piece of taffy or pizza dough. It doesn't snap cleanly, it thins in the middle, weakens, and eventually tears open along a line. That's what the new model suggests is happening to the lithosphere underneath Yellowstone. It's being pulled thin and torn open, and that tear becomes a channel, a pathway that lets melted rock migrate upward far more easily than ever could through an intact, unbroken plate. This is also the explanation for that strange, lopsided shape researchers keep measuring. It isn't a dot because it was never a single blowtorch the way Hawaii's hotspot is often described. It's a seam. That's why the heat signature leans southwest, because that's the shape of the tear itself. This finding effectively closes the book on the old movie version image of Yellowstone. A gigantic, glowing underground lake of magma just waiting beneath the surface. That lake was never there. What's actually down there is something geologists call a magma mush, mostly solid crystal structure, with liquid melt sitting in the gaps between crystals. It isn't a swimming pool. It's closer to a slushy or wet sand if the water in that sand were molten rock. And you can't drain a slushy. It doesn't slosh, it doesn't surge, and critically, it does not erupt easily because mush is stiff and resists flowing. Here's the honest scorecard on danger, and it's worth being direct about both sides of it. This finding does not mean an eruption is coming. Researchers do not think Yellowstone is due for one, and that's a genuinely reassuring part of the picture, because a mush-dominated system is inherently harder to erupt than a standing pool of liquid magma waiting to blow. But flip it over, and there's a genuinely uncomfortable implication buried in the same finding. If eruptible, fully liquid magma only assembles briefly right before an actual eruption and then disperses again, that changes what a meaningful warning sign would even look like. The classic picture people have been told to watch for, a magma chamber slowly filling. Over centuries, the way monitored volcanic systems in places like Iceland demonstrably do, where you can track the chamber gradually refilling toward the level it reached before the last eruption, may simply not apply here, because that kind of slow-filling liquid chamber doesn't appear to exist beneath Yellowstone in the Fir, St. Place. Nobody has ever observed a supervolcano do this whole process from outside in real time, so this isn't a claim that Yellowstone is about to erupt. It's something quieter and more uncomfortable. The possibility that the field has been watching for the wrong kind of warning sign all along. It helps to be specific about what researchers do still watch, because that list hasn't been thrown out. It's just being reinterpreted through this new lens. Ground deformation, the very slow rise and fall of the surface across the caldera, is still tracked continuously through GPS networks. Earthquake swarms, clusters of small quakes that happen fairly, at Yellowstone are still logged and analyzed for any unusual pattern or migration. Gas emissions and changes in the chemistry of the park's hot springs and fumaroles are still monitored as well. None of that monitoring stops or becomes useless because of this new model. What changes is the interpretation underneath it, the working assumption about what a truly dangerous signal would actually look like if this magma mush framework is the accurate one, rather than the old liquid chamber picture. Now, for the part that's genuinely fascinating on its own, separate from any question of danger, where is this thing actually going? Draw a line southwest from Yellowstone today, and you land in the Snake River Plain, a long, flat, strikingly straight scar running across Idaho. That plain is a trail of dead calderas, essentially a string of old Yellowstones. The hot A's pot has been burning its way northeast across the continent for roughly 17 million years, leaving one collapsed, exhausted caldera after another behind it as it goes. Wyoming, right now, is simply its current address, the latest stop on a journey that's been running for tens of millions of years. It's worth pausing on just how long that trail actually is. 17 million years is long enough that the hotspot has effectively been stationary in one frame of reference, while the North American continent has been sliding slowly over the top of it, roughly southwest to northeast, dragging a chain of calderas behind it like a scar left by a stationary torch under a moving sheet of fabric. Each one of those older calderas along the Snake River Plain went through its own version of the exact same process now happening at Yellowstone, filled, and eventually erupted or went quiet, before the system moved on to burn through the next stretch of crust to the northeast. Yellowstone is simply the most recent and currently active link in that chain. For that entire stretch, the system has been burning through crust that was relatively warm and relatively thin, essentially an easy path, a soft target. But directly ahead of it, to the east, the crust changes character. It gets colder, harder, and considerably thicker. And what that means going forward is genuinely an open question with two very different possible answers. One possibility is that a thicker, colder lid smothers the whole system. Heat spreads out instead of concentrating, and the hotspot gradually loses momentum, eventually going quiet on a geological AL timescale. The other possibility runs the opposite direction. A thicker, colder lid can behave like a pressure cooker, sealing off an escape route the heat used to have, building pressure instead of releasing it gradually. Nobody currently knows which of those two outcomes is more likely, and that genuinely is the state of the psi. Hence right now an honest, if slightly uncomfortable admission that the future of the system depends on a mechanism researchers only just discovered they'd been misunderstanding. As one of the study's authors put it, the plumbing underneath this system turned out to be different than anyone assumed, and that means every existing model of a future eruption needs to be rebuilt around this new understanding. Take a step back and actually sit with what just happened here. A team of scientists ran the numbers on the single most studied volcanic system on the entire planet, a place with more seismometers, more sensors, and more published research than almost anywhere else on Earth. And the textbook picture, the one everyone has carried around in their head for decades, turned out to be pointed in the wrong direction entirely, not slightly off, not a minor correction. The heat was assumed to be rising straight up. It's actually moving sideways. What's genuinely unsettling about this isn't that Yellowstone is somehow more dangerous than people thought, because the honest reading of this research doesn't support that conclusion. What's unsettling is what it reveals about how thin our confidence in these models actually was to begin with. Researchers had a sense that something in the old description didn't quite fit for years without the tools to properly resolve it. And that's worth remembering anytime a headline confidently tells you exactly how a system this deep, this complex, and this fundamentally invisible to direct observation is going to behave. Everything anyone knows about what's happening, miles beneath the surface of the Earth, is built from indirect measurements, mathematical modeling, and simulation, not direct observation, which means all of it remains provisional, capable of being revised the moment better tools and better models come along, exactly like what just happened here. The ground underneath Yellowstone hasn't changed because of this study. It's been doing whatever it's doing for millions of years, regardless of what any model says about it. What's changed is the picture in scientists' heads, and by extension, the picture the rest of us have been carrying around too. That's genuinely the more interesting story here. Not that a supervolcano got scarier overnight, but that one of the most intensively studied places on the planet just quietly proved how much of what we thought we understood about the deep Earth was still, at its core, an educated guess waiting to be tested. So where does that leave things heading forward? Researchers will now be working to reconcile this new mantle wind and lithospheric tearing model against the existing seismic and deformation data collected over decades at Yellowstone, testing whether this framework can better explain the swarms of small earthquakes, the subtle ground deformation, and the periodic changes researchers have already been tracking at the surface. It also opens a genuinely new question for volcanic hazard science more broadly, because if the classic warning sign of a slowly filling magma chamber doesn't reliably apply to a system built around a mush and a tectonically driven tier rather than a persistent liquid reservoir, then researchers studying other supervolcano systems around the world may need to revisit their own assumptions about what early warning actually looks like in a system like this. None of that changes the bottom line. Researchers themselves have been careful to state plainly, this new understanding does not mean an eruption is imminent, and it does not mean Yellowstone has become more dangerous as a result of this study. What it means is that the underlying plumbing of one of the best studied geological systems on the planet turned out to be fundamentally different from what nearly every diagram, textbook, and documentary had been showing for the past 50 years. And that difference is significant enough that every existing model of how this system might eventually behave now has to be rebuilt from that corrected foundation. That's really the story here. Not a countdown to an eruption, but a genuine, humbling correction to how scientists understand one of the most closely watched geological features on Earth, and a reminder of just how much of what sits beneath our feet is still, honestly, an open question. If there's one thing worth carrying away from all of this, it's that being wrong for 50 years about the basic mechanism underneath the most studied volcanic system on the planet isn't a failure of the scientists who built and believed the old model. It's exactly how good science is supposed to work. The mantle plume theory wasn't a careless guess. It was the best explanation available, given the tools and data researchers had at the time. And it held up reasonably well for decades precisely because it explained the one truly strange thing about Yellowstone, a volcano sitting in the middle of a continent instead of along a plate boundary. What changed wasn't the ground. What changed was the resolution of the tools available to actually test that explanation against reality. And once those tools existed, the old picture didn't survive contact with better data. That's not a scandal. That's the process working exactly as it should. And it's worth remembering the next time a confident diagram or a decades-old textbook explanation gets treated as the final word on something this deep, this complex, and this far beyond direct observation.